one observation is that this is what we saw last class, is that at a phase, at T and P, consistent with a phase transition, so at the melting point or the boiling point, we saw that delta G for that process is equal to 0. We looked at for water, right? We saw that the delta G for water vaporizing at 298 Kelvin had a positive delta G, but when we warmed it up to 373, the boiling point, G switched sides to negative. So the boiling point, the phase transition, if you will, occurs precisely where delta G becomes 0 at a given temperature and pressure. All right, so one of the questions we need to ask now is, say for instance, given a value of P or T, let's say T, what pressure do we need such that delta G for the phase transition is 0? Okay. Of course, we know for water, right? We know for water that water boils, we know a TP, if you will, for water. That water, for instance, has delta G equals 0 and T is 373 Kelvin, 100 C, and 1 bar of pressure, right? Atmospheric pressure. But what about the boiling point of water on Mars, where the atmospheric pressure is a fraction? I don't know what the atmospheric pressure of Mars is, like a torr maybe. It's 1,000th of an atmosphere maybe. Or maybe we're on Jupiter, where the pressure is 10 or 100 bar. Or maybe we're in the vacuum, right? Or maybe a really good one is if you're an organic chemist, you've got some mixture of your material, some products that you want to separate and isolate, but you've got this low boiling solvent. Maybe Dr. Trilla made you use acetonitrile or dimethylformamide, something that's got this really high boiling point. It's really hard to boil the solvent off. So what we need to do is figure out how to take our samples conditions and set them so that we can achieve boiling. Right? And so the way we do that with high boiling solvents is that we put our flask on a rotovap, right? And you apply a vacuum, a suction to your sample. So you create your little flask is now at low pressure, and what happens? Well, the boiling point of your solvent drops. Right? And if you, for instance, you have ether, it's a really great example where ether or dichloromethane, something very high boiling, very volatile. At room temperature, you put that flask on to the rotovap, apply a steady, constant vacuum to it, and suddenly that dichloromethane or that ether begins to boil at 25 C spontaneously. Right? It removes itself. Right? So there's a way to trick, right? You don't have to be at 100 C to boil something. You can change the pressure to lower or higher to change the boiling point. All right, so I want to think about that, right? Maybe that's a good kind of target is how do we know, how can we predict and calculate where the boiling point is for any material or the melting point or whatever as a function of temperature and pressure. And so the observation, I'm just going to write this here, is that a solution on a rotovap has a lower solvent boiling temperature than the solution at 1 atmosphere. Right, so the boiling point's a function of temperature and of pressure and temperature. If you think of boiling point's a temperature, then it's a function of pressure, right? And so what's the functional form of that, right? So for a given material, how does the boiling point or the melting point vary as you change the conditions? Right, so we want to construct something, we want to come up with an equation or some sort of instruction that allows us to calculate precisely kind of how the boiling point moves in temperature and pressure space as you move through the space of temperatures and pressures. So our goal here is to construct a diagram of the T and P values for a material, for a molecule, that satisfies delta G is equal to 0 for a phase change. Right? We want to think about where are those, right? How does that curve move as a function of pressure and temperature, right? The boiling point or the melting point. And the term for this kind of diagram, very self-explanatory. You've probably seen them before. It's called a phase diagram. All right, I'll show you an example of a phase diagram right now. So let's look at the one for water. I think this is something I didn't do last class, which is show you one first. It said we derived it first and showed it. So let's look at it first. So we'll look at a very simple water system, a water, what's it called? Phase diagram. Thank you. So really, really simple water phase diagram. I would really like one that's not logarithmic. This one's nice. Let's use this one. Let me make this a little smaller. All right, so here's a phase diagram. This is what I mean by a phase diagram. And this is a phase diagram of water. Let me make it small enough so that we can all look at it. Okay, there we go. All right, so what do we see here? Again, maybe you guys have seen these before. What we have is a curve of pressure. It's in kPa, kilopascals. Just FYI, 101 kPa is 1 atmosphere. I'll write that if you don't have that. That's kind of a random conversion. This is 1 atmosphere. So let's look at what this tells us. All right, so let's just kind of, right, so these curves right here that you see in the phase diagram, black curves, are these lines of delta G equals 0. So if I go to a certain temperature, let's say 100, and I find where that vertical line meets my phase diagram right here, and this will tell me exactly the boiling point of water, right? Because it's the boundary between gas and liquid. It's up here, gas is down here. And that temperature, again, 100 C, I move over, okay, it's 1 atmosphere, exactly like we expect, right? But as you can see, as the temperature goes down, the boiling point also decreases. Not surprisingly as well, as temperature increases, as the temperature goes down, the required pressure to boil goes down. Right? So the boiling point decreases as a function of pressure. The boiling point on the x-axis decreases as a function of decreasing pressure. And everything should make a lot of sense here, right? And again, where the boundaries are, where all of these phases are, also makes sense, right? Gases tend to be dilute and hot, right? Gas tends to exist, vapor tends to exist in hot environments, in low pressure, right? Where the attractions don't win out, overheat. So the gas fills the bottom right of the phase diagram, right? The whole hot region and the low pressure region. At intermediate temperatures, we raise the pressure, and we saw this exactly in CO2. Intermediate temperatures, we raise the pressure and the system starts to condense. So liquid's up here, directly above. And of course, if we get high enough pressure, cold enough, those attractions between the molecules are so significant that the system condenses into a solid, freezes out. And so ice almost always fills the kind of top left side of this expression, the low temperature, high pressure side. So I always like to think of, and there are very few exceptions to this rule, that liquid is intermediate P and T, gas is high T, low P, and solids are high P and low T materials. Okay. And that's generally the case for most materials. Right? I can show you the graph of benzene, for instance, or any other material. And you'll see that a few things change, right? For instance, where the lines, the curvature of the lines and where the intersecting points are will change for the material. But by and large, the graph for benzene doesn't really look any different than this. Okay, so the values of things are changing, but the shape of it is very similar. Okay, so most materials act like this. So what I want to do today is to come up with an equation that allows us to precisely calculate these lines, right? Maybe you have a new material. You want to measure the new material. You don't have one of these to look up on Wikipedia for your new material. You want to calculate it yourself. This is something you do in lab, solid liquid phase diagram. In this current rotation, you're doing precisely that. Now, in the solid liquid phase diagram lab, your curve is purity of naphthalene or biphenyl on the x-axis and temperature on the y-axis. But that's because you're at constant pressure, right? So with the biphenyl naphthalene, you're basically doing a vertical cut. Horizontal cut at a constant pressure of your phase diagram of the naphthalene example, right? Because you're not varying pressure there, just temperature. We'll look at mixtures hopefully next week a little bit more. So I want to go and calculate. Let's look at a couple of interesting points on this curve, and we'll dig into them a little more seriously next week. But there's a couple of interesting points in here. First, we have the curves between all of the layers. But there's 2 points that I want to point out, which are already marked here: triple point and critical point. There's this point right here, triple point, where all three of the materials coexist. So if I jiggle the temperature or the pressure one way, I end up in the, right? If I'm at this temperature and I pressurize it, I end up in a liquid. If I depressurize and expand it, I go into gas. If I cool it a little bit, I freeze it. Or if I warm it up at constant pressure, I vaporize it, right? So all three at the triple point, all three of all the possible phase transitions have delta G equals 0. So there are three. Let's talk about the different types of phase transitions. So just some nomenclature. Gas to liquid is called condensation. Liquid to gas is called vaporization. Solid to liquid is called melting. Does anyone know what liquid to solid is called? Does anyone know what that's called? Someone's going to say freezing. It's not freezing, unfortunately. Sublimation. No, that's not sublimation. That's the other one. I haven't listed yet. The chemical term for this is called fusion. And then what's sublimation, guys?
Solid to gas.
Solid to gas. Yeah, that's right. When your turds turn into poop or farts. That's right. Sublimation. That was a really inappropriate reference. I'm sorry. That's the first thing I think of, other than iodine. Of course, iodine is a material that has a sublimation transition at atmospheric pressure. So you can't. It's really hard to make liquid iodine. It's really easy to make gas and solid because you sublime at room temperature. All right. So the nice thing about the triple point is that the delta G for all of these is 0 at this point. Delta G is 0 for all of them. They're all at equilibrium simultaneously. One of the things that we'll learn next week is what's called the Gibbs phase rule, another great contribution from our New Haven rotting corpse, is that every pure material has a triple point, okay? It's guaranteed. Where that triple point is entirely dependent on the molecule. Water's triple point is at about 0.6 kPa, right, really low pressure, and about 0 Celsius, right near freezing. But benzene's triple point is somewhere very different, right? But they all have triple points, guaranteed to have a triple point, all pure materials. They always exist, always an intersection of all 3 points. The other one I want to introduce is this critical point. We're going to look at this very, very carefully, hopefully next Thursday. If not, it'll be the next Tuesday after that. Things start to go really weird here. Because what do you notice here? There's the reason why the coexistence curves ends there. Right? It doesn't go, the coexistence curve between liquid and gas does not extend forever. There's a point where it stops. Right? And we saw this in the compression curves for CO2. Any temperature above the critical point that I've written here, 31, acts like a gas, right? I can just feed, at 50C, I can just feed in gas to my heart's content, and it will never condense. At 36C, I can feed in gas, and it compresses a little funky, but it will always just be a gas, no matter how much I have. There will be never a liquid transition. It's not until I hit 31 Celsius for CO2 that I start to get condensation. So there's a specific temperature where coexistence between liquid and gas begins. And there's past that temperature, there is no difference between the liquid and the gas. So liquid only exists in a very certain region. And we can kind of understand that intuitively because our claim was the reason why this liquid forms in this region is that it's in a condition where the intermolecular attractions between the molecules in the gas are sufficient enough to dominate over the heat pushing them apart. And the system contracts and condenses into an attractive liquid. But once you crank the heat up high enough, there's so much damn heat in there that regardless of the amount of material in there, there's enough heat energy that the attractions will never dominate. So any point past 31, you have too much heat in there for it to ever condense. Okay, so liquids technically only exist for a small range of values. And you can see that here on the phase diagram, that beyond 374 Celsius and 22,000 kPa, which again is an insanely high pressure, there is no more liquid. The coexistence curves ends. Out here, there's some fluid that kind of, if you look at the picture, it could be liquid, it could be gas, might be a mix of the two, but there's not two phases anymore. There's only one phase. So the critical point is this magical place where our concept of gas and liquid ceases to occur. So this is end of gas-liquid coexistence. Only one fluid phase exists. So the type, these fluids that exist beyond the critical point have a special name. Fluids beyond the critical point are called supercritical fluids. If there's anyone really into green chemistry, you may have heard of supercritical fluids before. It's kind of a weird concept because for instance, to create a supercritical fluid of H2O requires you to be at 374 Fahrenheit Celsius and an insane pressure. Right? This is 2200 bar, right? 2200 atmospheres. That's a lot. So you have to pressurize water and heat it up, and then suddenly the difference between water gas and water liquid ceases to exist. They're the same fluid. Right? We'll look at this very carefully because it's kind of a weird phase transition. Right? Imagine that you sit on this line and you just travel up this line with your water sample. Right? What do you see? Well, along this line, you see a mixture of water and gas, right? Because you're on that coexistence line, they live in equilibrium together. So your flask, if you will, your vessel, will have a little bit of liquid and a little bit of gas as you travel up this curve. But when you hit the critical point and you go look at your material, you only have one, right? Let me start over. Here you have two phases, right? You have two layers. You have a gas layer of low density and a liquid layer of high density. And then when you get to the critical point, you only have one layer. And they're both of this, it's a one density, it's a one phase system. The gas and the liquid somehow have morphed into each other into this kind of intermediate fluid called a supercritical fluid that is only one layer, only one phase. So you can almost imagine that if you think about your system here, you're in a two-phase system here, and then suddenly you undergo a transition into one phase. Right? So that may be a phase transition as well. Right? I'm going from a system that has two layers to one that's one, spontaneously. Right? So this might be a phase transition as well, in a different way. So again, the way that we know phase transitions is going like this, across the boundary. But if you follow this curve, you just kind of sneak by the critical point, and then suddenly you've gone from two phases to one phase up here. I'm sorry, that's not really well drawn. But so somehow we've undergone some weird transition from 2 to 1, but we haven't crossed the boundary at all. We're still on that delta G equals 0 line, but somehow we've transitioned into a region that's now one phase, not two. So this is also a phase transition, but it's kind of funky. It doesn't really quite do the same thing as the liquid gas and the ice solid, where you're kind of moving across the boundary as you freeze or vaporize. This is you're just writing it, and then suddenly you don't have two phases anymore. You only have one. Right? This is true, once again, for all materials. Every material has a critical point. Every liquid has a limit. And once you pass that limit, there's no difference between liquid and gas. You only have a supercritical fluid. And it turns out the mathematics and the physics and the chemistry of this beam is beautiful. And it's actually related to the same concept of magnetism. The process of a metal becoming magnetic is precisely the same phase transition as this critical transition as well, from 2 to 1. Right? I'll show you that next week. It's really, really cool. So we're not going to focus too much on the critical point today. I really want to focus on these lines here, right? Because that's what we really appreciate the most, and what we do the most is, freeze stuff and melt stuff and vaporize stuff. So I want to come up with a way to calculate these lines. And what we'll see is, again, one of the questions you should ask yourself, of course, is why are they curved this way? Why is the gas-liquid line like this, and why is the solid-liquid line like this for water? Right? So let's answer that question. Why do these things have the shapes that they do? So we're going to do a little derivation here today. We'll come up with this really lovely equation that'll actually tell us exactly how to calculate these curves to precision. Really, really simple argument. Okay, so let's use the fact. So let's again remember that at a phase transition, that delta G, which is the G of the final phase minus the G of the initial phase, is 0. Okay. So what I want to do is I want to think about, so what we have here is some equilibrium here where our Gibbs energy is 0. And so what if we vary Gibbs energy a little bit? What if we jiggle our temperature and pressure a little bit, jiggle our parameters for Gibbs energy, and let the system equilibrate, right? So every change that we make with G, if we're at equilibrium, that jiggle will kind of come back to 0, and we can constrain it. So what we can do is write this. Remember G again, remember that G is a function of our chemical ensemble, MPT. Right? Those are the parameters we care about in chemistry. So we could write that the change in delta G looks like the derivative of delta G with respect to temperature at constant pressure, dt, plus the derivative of delta G with respect to pressure at constant temperature, dP, plus the derivative of delta G with respect to the change in the moles of the material, dN. This is at constant Tp. Right? And I showed last class that that this derivative is minus S. This derivative is volume. And just like this one has always been, this is what's called the chemical potential. Which we call delta mu, or just mu. Okay, so that means that the derivative that gives energy varies like S minus S dt plus B dP plus mu dN. Okay, so this whole change, right? We're at equilibrium, right? So that means G is 0. We're sitting right in that minimum of energy. And so if we push the energy up a certain direction, the energy is going to roll back down like a ball down a hill. If we push it the opposite direction, it's going to roll back down to the minimum. So if we make any jiggles, the net jiggle we make at equilibrium is 0. So this whole thing is 0. All right, and so now when we move G, like we're moving over that little phase transition line, the Gibbs energy can change as a function of temperature, pressure, or the number of moles. All right, but we're at a phase transition. So we can actually make an even bigger constraint here. So we're along the phase transition line. At T and P. So at this line, we can say that dt and dp are 0. Right? So the only thing that's really changing when we sit on that equilibrium point when we want to jiggle G is the number of moles of our two phases. So what I need to write, so now we actually can use this chemical potential. So let's take this now. So the only term that's remaining is that mu dN is equal to 0. And so now we have two phases and two materials, right? We have our final phase. So we have material, what do I call it, I, with N sub I moles, and chemical potential mu sub I. And we have material F, which is our final material, which would be, like, say, liquid and gas. We have 1, and then we have 2. Material J. N sub J moles, and chemical potential mu sub J. And so when you plug this in, you have to take the whole sum of all the chemical potentials and changes. And what we get is that mu sub I, our chemical potential, times the change in the number of moles of our initial phase, plus the chemical potential of F, times D and F, is equal to 0. And I'm just going to rewrite this. It says that mu sub I d n sub I is equal to minus mu F d n sub F. All right, so let me explain what this means. I've gone through a bunch of math, and let me talk about what this equation tells us. So let's look at the units of this chemical potential. The left-hand side of the equation is delta G, so the whole thing should have units of energy. N has units of moles, right? So the chemical potential times the number of moles should have units energy. And the only way for that to be is that chemical potential has units of energy. Chemical potential is an energy. This has units of, say, joules per mole. Or joules if we're not working in moles. So this is an energy of some sort. It's a potential energy. And what we get is an equilibrium where both of the phases, you're equally likely to be in either of the phases. They both have the same energy, delta G is 0. What it says that is that the chain, as molecules move from one phase to another, so let's say, for instance, I is the liquid and F is gas. Okay, so we're boiling, for instance. It says that the change in the moles of the liquid is equal and opposite to the change in the moles of the gas times this proportionality factor, mu. The idea is that the liquid and the gas have different costs to removing molecules from them. Okay? The gas, for instance, it might be easier to pluck a few molecules out of the gas to put it in the liquid than it is the other way around. So the chemical potentials tell you what that cost is. So for instance, if it cost $1 to remove a molecule of gas or liquid, and it costs $2 to remove a molecule of gas, so is that the way I do? Yeah, all right. Then that means if I move one molecule of liquid over to the gas, then the gas is only going to return half a molecule back because it costs twice as much. Okay, so the chemical potential in some ways is the cost or the benefit, an energetic cost or benefit, of making moving moles from one phase to another. So if I make $1 right, some energetic cost of transferring molecules from I to F. Right? So if it costs $1 per one molecule and it costs $2 here and I move one molecule over, then I only get 0.5 molecules on this side, right? So if there's more cost to moving a molecule one side or the other, you have an unequal balance of motion of molecules. Right? You might get more in the liquid than you get in the gas, so it won't be 50-50 necessarily, but rather the distribution of gas molecules to the liquid molecules is based on the ratio of the two chemical potentials, right? The cost. Now, it also could be negative, right? Right? And the cost, the Mother Nature could give you money back for giving away molecules too. It might charge you, but it also might give you money back. If it doesn't want the molecules to be somewhere, it's going to give you energy back by removing them. Okay, so the chemical potential is that cost. What we're going to see is that the chemical potential, in fact, we're going to see when we get to equilibrium. So I'll write this as spoiler. The chemical potential of a material is the same as the Gibbs energy of that material, which is going to be the enthalpy of formation of that material minus T times the enthalpy of the entropy of formation of that material. Right, so the Gibbs energy of each material, right, we get the formation enthalpies and entropies. That'll tell us kind of how willing the system is to pluck molecules away from one system or the other. So if the system has a really, really negative Gibbs free energy, right, it's really, really stable, that means it has a really, really negative chemical potential, and it's going to be really hard to pull any molecules out of there. You got to put a lot of energy into the system to pull molecules out of that stable phase into an unstable one. All right, so these tell you something about this balance between stabilities. All right, so that'll play a big role in equilibrium, of course. If we have a product that's very stable compared to a reactant, and you have some random mixture of the reactants and products, as you go to equilibrium, it's going to be really easy to pluck molecules out of the unstable well and put them in the stable one. Right? The chemical potentials tell you the direction of that motion. All right, we'll practice these. We'll see them multiple times. Chemical potential is one of those concepts that is underlying everything in chemical equilibrium. It's just one of those things you don't really get to appreciate until much later, and it takes a little bit of practice and understanding to work with it. Right? But this is where the chemical potential comes in, because now we're in a situation where temperature and pressure aren't changing. Right? So delta G is a function of those as in moving, but obviously at phase transition something is moving. Right? There's some sort of energetic transfer during a phase transition that isn't temperature and pressure, and that's just the heat or the energy of moving, say, unstable gas molecules into a more stable liquid phase or vice versa. And all of that energy comes from the motion of molecules moving from one phase to another, which is the chemical potential. It's the chemical energy of the system. All right, so what we actually call this, right? Remember that when we go back to the old style way of talking about things, heat and work, right? This is heat. This is mechanical work, BDP, right? The physical motion of something pressing against the walls. And this mu dN is what's called chemical work. It's the amount of energy that a chemical mixture invokes or causes, the energy change that a chemical mixture causes when it equilibrates by moving molecules from one phase or one material to another. Okay? But when we get to equilibrium, we start doing reactions. Obviously, the chemical work is going to play a big role because we're going to be balancing between mixtures of products and reactants, and that evokes, as those move, that evokes a change in energy. Okay, so we have this equation here that the chemical equilibrium, or sorry, the chemical potentials are balanced. That as one increases in material, the other one decreases equivalently in material. Just a second. Okay, sorry. Just needed to read something. Okay, so now we're about halfway to our useful equation. Just a little bit more work to do. All right, so the most important thing is that at equilibrium, delta G is 0, of course. And what this actually means in reality is that the chemical potential of the one phase is equal to the other phase. Or sorry, the change in them is equal to, sorry, D. All right, so if delta G is equal to 0, then the change in those are equal to 0. All right, so we can now approximate the change in du as a function of temperature and pressure. So now we're going to jiggle our things and see how the chemical potential changes. This is d mu dt, constant p, dt, plus d mu at constant p, at constant, sorry, dp, constant t, dp. Right? But what did I just write above in my spoiler? That U is the same as the Gibbs energies. So this is equal to dg dt at constant p times dt plus dg dp at constant t dp. But I already wrote down what those were, right? This right here is negative entropy, and this right here is the volume change, or the volume of the system, the inverse density, the molar volume. All right, so once again, we've returned back to that Gibbs equation that we started with in the first place. And so if I take this equation, right, so if I take now delta mu, which is equal to delta G, which is equal to 0, right, and then I rearrange terms. I get a really, really interesting equation. I get that the change in chemical potential, which is 0, is equal to the change minus the change in entropy, dt, plus the change in volume, dP, okay, which says that delta V, change in the volume dP, is equal to the change in entropy dt. All right, let me stop here for a second. Because what are we trying to aim to get, right? We want to think about the curves where delta G or delta mu is 0 along T and P. Right? So what I want to think about is how do I calculate that curve? Well, that curve is a function P, pressure is the y-axis, and it's a function of T. So if I can calculate the derivative dP dt, that tells me the slope of the curve at a certain point T and P. Right? And if I integrate that dt, if I take that derivative dP dt, which is the curve of the coexistence line, the slope of the coexistence line at a certain point, and I integrate it from t equals 0 to t equals infinity, I get the function p of t. Okay, so I just need to rearrange this equation. I'm just going to jam it back here because we have one more manipulation that I want to do. Let me put it up here. I'm sorry. I'm sorry that I'm so messy today. Right? It says that dP dt is equal to delta S of the phase transition divided by delta volume, right? The volume or the density change of the transition. So let's hold on to that for just a second. I'm just going to copy and paste this over so we can continue where we were. I know this is a lot of math, but we're getting to the answer in just a second. So we have this equation here that at the coexistence line, the slope, so what we have here is at, let me write it up here. So this is along the coexistence line. The slope of that curve, which is going to be pressure of temperature, function pressure of temperature, that the slope of that curve at some temperature and pressure is the change in entropy divided by the change in the density or the molar volume of the material. But we can do one better than that, right? Because what's the problem here? Well, it's easy to measure change in density, right? Because remember, 1 V bar, molar volume is 1 over the molar density. So it's easy to measure density. You just fill it up and measure how much volume it fills, right? But it's hard to measure delta S. But we can make one simplification here. And once again, recall delta G is equal to 0. And remember the definition of delta G, delta H, T, delta S. And so that means delta S is delta H over T. Or we can make that substitution. So now we have this equation that says the slope of our coexistence line at a certain point is equal to the enthalpy of that phase transition divided by T delta V. All right, that was a lot of work. But here are three things that we can three things that are really, really easy for us to measure. The heat change across the phase transition. You did this in solid liquid phase diagram. You've done this in calorimetry. You know how to do this. Delta V, of course, is easy. You just measure how much 1 gram of material fills up. Or how much volume 1 gram of your material fills up of each of your phases. And then at the temperature T. Right? And this gives us the slope of the curve at a given point T and P along the line. This is called Yeah, I always get confused. This is what's called the the Clapeyron equation. Okay. So as long as we move along that curve, we measure the heat of that phase transition, and we measure the change in the densities at that temperature where the phase transition occurs, and we know exactly the slope of the line at that point. It's very powerful. We can rederive the general viewpoint, the general appearance of these phase diagrams by just thinking about how does delta H and delta V move across normal phase transitions, right? Because every liquid solid phase transition is almost exactly the same. They have roughly the same sign on the change in delta V, the same sign on delta H. So we can predict whether the slope as a function of t is going up or going down. Right? And that allows us to qualitatively construct the curve. Right? So let's do that. Let's just kind of look through our different phase transitions and think about what does the slope of the coexistence line look like at that point. So we'll make a little table here. So first we'll have the final phase, the initial phase, right? We'll think about the sign of delta H of that transition, and we'll think about the sign of delta V along that transition. Okay, so let's try a simple one. All right, so let's do gas and liquid. All right, so we call that vaporization. All right, is delta H for vaporization endothermic or exothermic? Does it have to absorb energy or release energy? Absorb, right? Because you got to break those bonds in the liquid, right? So delta H is positive here. So I'm just going to write greater than 0. Because we only care about whether it's increasing or decreasing as a function of temperature here. Right? I'm not even worried about the value of it. That doesn't matter here. The values are material dependent. All right, so what about delta V, right? Well, this is the same as the change in the densities, 1 over the densities, which is going to be 1 over the density of the final phase minus 1 over the density of the initial phase. Okay, so let's think about that. The final phase is a gas that has low or high density. Which one? Compared to the liquid? Low. So we have 1 over a small number minus 1 over a big number, right? Because the density of the liquid is larger. So that's 1 over a big is a small number. And so it's a small number minus a big number. This is negative. Do I have that right? Hold on a second. Do I have that wrong? I'm sorry. I got to think about this for a second. Should be pop. Initial phase liquid. Liquid to gas. Gas has. I have this wrong. I'm sorry. I have it reversed. Didn't do my algebra right. It's the same as PI minus PF. All right. So let's think about it in terms of molar volumes. Maybe easier. Remember, molar volume is how much volume does 1 mole fill up. All right. So a gas has a large molar volume, right? Because it takes a lot of space to put a mole in. And right. So let's take it for instance for water. Right. Ideal gas for 1 mole at room temperature fills 22.4 liters. 1 mole of water in the liquid form fills 18 milliliters. Okay, so delta V is positive here. Right? The gas has a much larger molar volume. Right, and what does that say? I forgot to add one more. So we'll just say instead of here, final, we'll call this dPdt, the output. Right, so the slope of the curve along the gas-liquid coexistence line is positive as well. All right, let's go look at just go back a page and go look at our phase diagram real quick. right? And we can see exactly that, right? Along the gas, as we go up in temperature, the value of the pressure of the phase transition increases as well. The slope is positive. Now we can also make an estimate about how sharp the curve is, right? How sharp the curve is, right? That's going to be something about how fast it rises. Right? And of course, liquid and gas, liquid is fairly dense, and gas is very not dense, so delta V is large, right? So delta V is much greater than 0, right? And so that means dP dt, right, has a number of some sort here divided by a big number on the bottom, so the slope is shallow, right? So this is a shallow curve, or at least relatively shallow. Okay, we kind of saw that, right? If you saw that in a curve, go back to it, right? It kind of grows slowly as a function of temperature. So let's try another one. Let's look at solid and liquid. Right, so this is freezing. Right, so what about the enthalpy of freezing liquid? Endothermic or exothermic? We're going from liquid to solid here. Freezing is endo or exo? Who's done the phase diagram lab yet? What direction does your temperature go when it freezes? Down. So what does that mean about the heat of the system? Is it releasing heat or absorbing heat? Releasing. So it's exothermic. Now what about delta V? So our initial phase is liquid, which has an intermediate molar volume. Right? It takes some amount of space to fill to get a mole in, right? Some amount. And the solid, of course, is generally more dense, right? We generally think that solid is more dense. So you have a more dense material which has a smaller molar volume minus a larger molar volume. So delta V here is negative. But what does this assume? What have I assumed here? Here have I assumed that the solid is more dense than the liquid. Does anyone know of an exception to this rule? Exactly. It's about the only example of this, in fact. So this is true for most materials except for one, which is water. It's water, right? Because what happens to ice? It floats to the top, right? Right? And when your ice melts, you pour a big glass of water all the way to the top of ice, and the ice melts, it doesn't pour over, right? Because the liquid is more dense than the solid. The volume decreases when you melt. So for regular materials, we have two negative signs for delta H and delta V. So dP dt for that phase transition is 0, greater than 0. All right? But for water, ice and aqua, we have a change sign for delta V. So dP dt for water is opposite. I'll show you that in a second. Right. And now let's think about the slopes of these really quickly, right? Compared to the gas-liquid one, right? So the gas-liquid one, delta V, is significant, right? Because the gas is much less dense than the liquid. But what about solid and liquid, right? What's the difference between the density of ice and liquid water? It's not really that much. It's like 10%. So here, so for solid to liquid, your density isn't changing that much. So your molar volume is not changing that much. So you have a small denominator, and therefore you have a very, very large slope. Very, very sharp. All right, let's go back and look at our curve now. Right. Shallow curve. That's positive for liquid gas, and of course for solid gas as well. It's the same argument. But for liquid solid, for water ice, we have a reverse slope, and it's also extremely shallow or extremely steep because delta V is very small. Okay. For our benzene, let's go look for a different material how it changes. I'll just pull up benzene's phase diagram. Now, I just typed in benzene phase diagram on Google image search, and the first result it has is benzene, picture of it, but it has the water phase diagram. It's incorrect. So let me find a better one. This one's good. All right, I'm sorry, this is potato quality, but it'll do. So this is one thing to know if people are making stuff up, if the signs are wrong. So here's a kind of similar basic benzene phase diagram here. And what do we see? Oh, I'm sorry, I'm stupid. Right, so this is benzene. Right? So for benzene, right, we see the same thing, right? We see a shallow gas-liquid coexistence curve. All right, and then we also have a sharp but positively oriented solidus line, liquid or freezing line, right? Most materials look like this, right? Water is the exception, because waters have hydrogen bonds, and the hydrogen bonds in the water just throw everything into it. Everything. And one of the reasons why, for instance, hopefully I'll have some time to do this, talk about water. Water has the reason why water is less dense is because of its hydrogen bonding. To get those hydrogen bonds aligned perfectly in the crystal, the waters actually have to be fairly far apart. It causes it to be less dense. Because the ice actually wants to pack in closer, but the hydrogen bonds want to be at a certain distance, and the hydrogen bonds win out, which make the crystal packing of water more looser than you would expect, and therefore less dense. But most materials want to crack in together as close as possible. Water is the exception. Okay, so again, we have to think a little bit about what I have here. Is a curve that is basically a slope that's basically a number divided by another number. And if we think about it, right, think if delta V and delta H are temperature independent, they're the same value no matter where you are in the curve, right? What that would mean is that as we go up in temperature, the denominator would get larger and larger because delta H over delta V is fixed at constant for temperature independence. So this would kind of look like 1 over T. Right, so you would expect actually that the slope of this curve would start to go this way, right? Because delta H over delta V is getting small relative to delta 1 over T, and 1 over T dominates, and so the slope should start going to 0 instead for large T. But it doesn't, right? It increases. Right? The second derivative is positive, not negative here. Right? So if, let me just write that here, if delta H and delta V are temperature independent, dP dt should go to 0 as T goes to infinity. But in fact, we don't see that, right? We see the line increase instead, right? Right, and so this is also proof that enthalpy is not enthalpy and volume. They're temperature dependent quantities, right? The density of water, and the density of liquid water, and the density of gas changes as a function of temperature, right? And so does delta H, as we saw, right? We saw that, but delta V increases with T, and delta H increases with T faster than T increases. Right? And we saw that right with the heat capacities, right? When we integrated the heat capacities, as T increased, delta H also increased. And it increased more rapidly than T, right? Because it had a T to the 3 and a T to the 4, right? It was a quadratic or a cubic function. So it's growing faster than linear. So at high temperature, those went out. Right? Because delta H gets larger for vaporization. Sorry, no it doesn't. It gets smaller. I apologize. I just forgot that. It gets smaller. Let me think about this for a second. So the effects of these is generally temperature dependent. And dominate over 1 over T. So dp dt usually gets larger as T increases. All right, so what's actually happening? Is delta H changes a little bit. What's actually happening is that the water, the liquid water, as you heat it up, is getting less dense. And as you heat up the gas, it turns out it starts to get more dense as you go to higher temperature. The pressure starts to increase. It gets to compress more. The density goes up. And so delta V, the difference between the molar density, the molar volumes of the liquid and water start to get closer and closer together. And so that makes the denominator smaller and smaller. And that's why this curve continues to kind of accelerate, if you will, as you go. Okay, and what's really interesting, we'll look at this more carefully in next class after the break, is that at this point right here, that the density of the liquid, well, let me actually write this, the molar volume of the liquid is equal to the molar volume of the gas. Okay, so what happens is as you climb up this curve, as I just said, the liquid gets less dense, and the gas gets slightly more dense as it gets closer and closer, higher pressure, higher temperature, it's more compressed. And eventually they reach a point where they're the same. All right, well think about it now. Do we have 2 layers anymore at that point? No, we only have 1 layer because both layers have the same density. Right, so at the critical point, what happens is that delta V goes to 0, and therefore dp dt goes to infinity. It diverges. Right, so at that exact point, the critical point, the density of the gas and the density of the liquid are precisely the same. They have this, and they also have the same energy, right? Because delta G is 0 at that point. So the liquid has the same energy as the gas at the critical point, and it also has the same density as the gas at the critical point. There's no distinction between the two. They form the same phase, they have the same energy, they have the same attractions, the same behavior. So at the critical point here, what this means is that coexistence disappears. And you only have one material. Because delta G is equal to 0, they have the same energy, and delta V is equal to 0. All right, so something's happening very, very interesting at this point. The reason why liquid and gas stop to coexist isn't so much necessarily that the gas doesn't condense anymore. It's just that the condensed gas has the exact same properties of the uncondensed gas. You can't tell them apart anymore. And as you go past that point, there's no distinction between them anymore. There's no more phase because the coexistence line has diverged. There is no more coexistence line anymore. The It's gone to infinity. There's only one phase left. The critical point is also some sort, as I said, some sort of phase transition, where we've gone from having two phases of two distinct densities, two distinct molar volumes, and we hit a point where there is no difference between the two. So why would we even consider them to be two phases if they give you all the same properties? All right. Next class, I'll show you a video of CO2 reaching this point, and you'll see exactly that. You'll see that you'll have a layer of liquid, a layer of gas in your CO2, and then as you climb this point, the critical point, the density of the gas starts to meet the density of the liquid, and then once you pass the point, there's only one fluid in there. There's no more gas, there's no more liquid, there's only one phase. All right, so by definition, once you calculate kind of how the density changes as a function of temperature, which we'll look at next class, and how the enthalpy changes as a function of temperature, you eventually hit a point where the derivative goes to infinity, it diverges, and therefore the system breaks down, the phase distinction breaks down, there's no more distinction between the two phases. Right? So we'll explore that point a little more carefully next class. And we'll find that, in fact, the dynamics at this point, the behavior at this point is far more interesting and far more impactful than anything else on the phase diagram. Okay? All right, you guys have a lovely fall break. I'll see you guys next Thursday. Just a few more lectures, and then we're going to pound out equilibrium and kinetics, and that'll be it.
Can I double check with you that I'm understanding?
I did the graph of the second derivative. So you said the second derivative where it's negative is where it's unstable. If you're looking at it
Yes,
from negative.
that has a positive second derivative.
So like did I graph the wrong thing? So like this is the point, the x point is like where it goes under, like where the y value goes under 0. So the second derivative. Like this would be like the x square root of.
That's correct.
Right? So
Correct. Oh, this is a plot of the second derivative.
yeah.
Oh, okay. I'm sorry. I thought that was a plot of your x versus f curve.
No, this is my
Oh,
second derivative.
that's right.
So I'm looking at where the second derivative
Right.
is negative. But then why is it also everything under? Or am I just looking at
No,
from
what it's
0 up?
what it's saying. So is this below TC? What it's saying is that any
It's the
whatever. I think.
Yeah, this is less than TC.
What it's saying is that every mixture between this 0 and this 0 is unstable.
Okay.
And all of these mixtures form stably.
Okay, that's what I thought. I was just confused because like the answer on the thing is that like x less than, so I was confused about why there wasn't
Oh, it's
anything
plus or
about.
minus. I'm sorry. Yeah, it's plus or minus. It's symmetric on both sides. Yeah.
No, everything is making more sense. And then I just want to be sure for 1.9, first you're asking them to find the J using this critical point.
Yeah.
And then when it says
Right.
it's critical temperature, like a different one, like not the one that we're assuming.
No, it's
Then-
450.
Oh, okay.
Yeah,
and then
that's where it
it's
breaks down.
The
Spinodal.
spinodal point, you want the X for that?
Yeah.
Okay.
The
so
idea is that let me clean up and I'll
Yeah.
try to explain this to you in a second.
I just, in the answer key, I didn't like see it.
So the idea is to
So I wanted to make
think
sure.
of this like a metallurgist, where you have a molten mixture that's a fixed mixture, say 60-40 mix, at like 1,000 Celsius,
Okay.
and then you anneal it down, and you want to make a stable 60-40 mixture at
Okay.
300 Kelvin, right? So you're going to bring this hot mixture and bring it down past a critical temperature.
Okay.
And the question
Yeah.
is how close do you have to be to 60-40 to get that layer at the right temperature? And the
Okay.
idea is that if your mixture is past the spinodal point at that temperature where 60-40 exists, then you won't make it.
So you calculate the
So it's
60-40
like-
thing, and then you
It's
use.
it's the distance. It's basically at 60-40. At that temperature at 60-40?